And I don't think there's any point waiting for people to join. They'll join us along the way, I guess. Yeah. So I've been looking forward to this class since. Why? Because it's electronics. And funny story, guys, calm down, calm down. I'm not, as I said, like I'm not going to cover, like I'm not going to go so deep that you people will now like be drifting and then it's now like, oh, I've lost you guys at some point. Don't worry, that's not what is going to happen. That's not what is going to happen. The class will be very fun and it's very interesting. I promise. I promise. I promise. You have my word. So I've been looking forward to this class because I mean it is electronics and it is very ironic because this time, how many this time Wednesday? I think uh this time I think how many years ago? This time like 4 years ago. I would have never said that, oh, at any point in time princess would like electronics because I saw it as something that was very, very intimidating. I was like, oh, electronics for them very, very, very smart people. Those are the ones that um those are the ones that like electronics. Those are the people that they shall used to get it and understand what is actually going on. But it's not for me. That's the mindset that I had. But then as the years went by, I don't even know when. I think it was 400 level IT, because it was then that I started seeing like the real life applications of electronics and all of that and all of that. That I now realized that, oh, this is actually very fun. And yeah, that was when like I now realized that electronics is actually fun. And it's not as what's the word I'm looking for here? Like it's not as complex and as intimidating as I thought it would be. Sorry, I'm trying to send the link to the other the other track of of embedded system. I've sent it to them. Okay. So I think that's enough for for backstory. And I'm trying to get a board. So sorry. I've set this thing up since. My bad. Okay. Blank board is what I need. Okay, so for this class, I prepared slides and then at a lot of points in time, like I'm going to be interchanging between the slides and a board because I'll need to do as as many be as much no as many illustrations as possible for this class because I like I like it to be that when I'm teaching you can see the full picture of what I'm trying to like explain to you. Yeah. So I'm going to be moving in and out of the PowerPoint presentation and the mirror board. Yeah, I'm going to be doing that a lot. So please just keep it in mind. And now I'll share my screen so you guys can see the presentation. I just thank God that I just thank God that I went out with this thing. Haha. PowerPoint, 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 PowerPoint. Okay, slideshow. Better. Okay, so you guys can see my screen, right? Okay. Okay, very good. These people that are joining, they're distracting me. Okay. Okay. So, welcome to YFE-ELECT 101. That's Introduction to Electronics. And it's going to be a very, please, at any point, if I'm moving too fast, just call it to my attention that, oh, please, can you slow down and go back? Because this is not a lecture, this is a class. And I'm not a lecturer, I'm a teacher. So, if at any point I'm going too fast, just let me know. And then I'll go back and explain again so that you guys can understand what it is I am trying to explain. Okay, so welcome to YFE-ELECT 101. In this class, we'll be dealing with Introduction to Electronics. I'm not going to go too deep because I just want to focus on the things that you guys actually need and not I don't want to go overboard and get carried away so that it's not intimidating, because I want to assume that let me just assume that this is everybody's first time dealing with electronics in the real world sense. So I'm not going to do anything that's I'm not going to teach anything that's so intimidating. But then if I do, because intimidating is relative, if I do, just call it to my attention. Yeah, I think I've said a lot and I've spoken enough. Yeah. So yes. So why electronics? Why is electronics so important? Especially since we're doing embedded systems and PCB design. Why is it important? Why do we need to pay attention to why is this class even necessary? And why do we need to know the fundamentals? This is because at the end of the day, every single thing that we're working with, the embedded systems, PCB design, whatever, as we saw in the last class, you are using a number of electronic, not electrical, electronic components to create your to design your PCBs before you eventually now say that, oh, okay, I want to have it manufactured and sent to the PCB manufacturing company, blah 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 blah. So why is it important? It's important because we don't want a situation whereby you now design a board. Because in the last class that we had for PCB design, we saw a lot of very beautiful and wonderful designs. We saw a lot of beautiful designs, and it just dawned on me that, oh, let's not skip the basics, because the basics, shade intended, the basics are very, very important, because if the foundation is not firm, like what's not the essence? So why electronics? Because at the end of the day, without it, life as we know it will cease to exist. Life meaning modern day life. We'll not have our phones. I won't even be able to talk to you guys the way like, oh, I'm in different parts of the world, or I'm in different parts of the country. How am I able to talk to you guys? It's because of electronics. Without electronics, it's not going to be possible for me to be able to do that. So, and we need to take every single thing into consideration so that whenever when we are eventually designing our boards or building our projects, we will not want a situation whereby, oh, somebody, where there are any accidents that could have been avoided because um we did not do the groundwork of having a firm foundation in our work. So yeah, so I'll be taking us through. I wanted to cover more. If we have more time, we shall cover like the other things that I had in mind for us to do. But these are the major things that we're going to cover today. And then if we have more time, if English, if we have more time, we will do more. English language. If we have more time, we'll do more. So yeah. So we'll cover what is voltage, what is current, what is resistance, what is power, what is pulse switch modulation, and then different type of yeah. So cover what is voltage, what is current, what is resistance, what is power, what is pulse width modulation, and the different type of sensors. Yeah. So let's go with type. So first and foremost is voltage. What is voltage? Let me now go to my drawing board. Let me go to my drawing board. So you guys can see my screen, right? I can see. Okay. Okay. Where is my pen? Where is my pen? Okay. So what is voltage? Voltage is basically pressure applied to a pressure applied to electricity in a circuit, or the amount of pressure applied to electricity in a circuit that is pushing it through that circuit, if that makes sense. So let me use real life example. I like to use real life examples a lot, so I'm going to do that. So imagine you have what should I use? Which example should I use now? Should I use the tank? Should I use the tap? Should I use this thing? Okay. So imagine you have a tap. Yeah. Imagine you have a tap. This how the tap is here. Yes, I think so. Please, if my drawing is ugly, don't laugh at me. My drawing is ugly, please don't laugh at me. Sure. You have a tap, and then you have, let's say, a hose attached to that tap. And then we all know that at any point in time when the way taps work, like as you turn the knob, I think it's clockwise. Yeah, as you turn the knob in the clockwise direction, you are increasing the amount of pressure applied to the water that is pushing the water from the tank, a bit from the hose, a bit from pipe that shall links the tank of the distance. That shall links the tank of where the water is coming from, the water supply, to the tap, and then the water now rushes from that tap to the hose. So the measure of the measure of pressure that is applied to this water that is from flowing from the tank to the tap to the hose is now your voltage in this situation, or pressure or your voltage. Sha. So imagine this hose now, or this tap is your circuit, and then the water that is flowing through it is your current. I'll explain what current is later. And then the amount of pressure that is now applied to that water that is now making it to pass through your tap, that is now what is known as voltage. Are we together? Do we understand? Okay. So yeah, that's in simple terms, that's what voltage is. That's what voltage is. So from voltage to current. From voltage to current. From voltage to current. Okay, so what is current now in this case? Current is the flow of or the rate of flow of electricity in a circuit or in a system. That is what current is. So now let's come back to this whole tap situation thing. I mentioned that um this water now that is flowing through tap, this water now that is flowing through this tap is the electricity, right? So the current now in this case is now, okay, how fast is this water flowing from the tank to the tap through the hose? How fast is it? So the rate at which this water flows from the tank to the tap to the hose in this case is now what is current. So the rate at which electricity travels through a circuit, that's not what current is. Understood? I think yeah, I think I've explained that as simple as possible. So now resistance. Resistance. Okay, yeah. Okay, I can actually rotate. I think I can actually rotate this thing. Okay, let's come back to this board. Let's come back to this board. Let's come back to this board and let's shift this thing out of the way. Okay, so what is resistance? I'm going to use another real life example now, and it is one of the examples I'm sure it's one of the classes. So imagine you are in the oh yeah, okay, imagine this is you. Imagine this is you, and then this is, let's say, what will I call it? Someone should give me any room in their house that I can use as an example. Any room in your house, can be your sitting room, can be your okay, kitchen. Okay. So this is you, and this is the kitchen in your house. This is you, and this is the kitchen in your house. And then this is the door to the kitchen. Please don't laugh at my drawing. This is the door to the kitchen. So now imagine you are now like, I believe all of us here have siblings. So in the, okay, imagine this is you, or imagine this is me, and then this is the kitchen in the house. And then let's assume now you now have like your siblings, whether your brother or your sister, but in this case, it's my sisters that can do this kind of thing. Imagine you're not trying to enter into the kitchen, and then your sister is now like at the other side of the door. Your sister is at the other side of the door. And you're trying to enter the kitchen, but then, and I know this is not possible because all of us are, I believe all of us are stronger than our sisters, like physically stronger than our sisters. So this is your sister, and your sister is trying to stop you from entering the kitchen. So what is she now doing? She's now applying force on this door so that you'll not be able to enter into the kitchen, right? Imagine normally, like if she was not there, you would have been able to enter the kitchen without any stress. You will just open the door and then you just enter, and then nothing will happen and nobody is disturbing your life. But now your sister now wants to do rough play. She's now at the other side of the door and she's using her leg, I'll be using her whole body and pushing the door shut so that you'll not be able to enter inside. Now, and then you now on the other side of the door is now like, I'm trying to enter the kitchen. Why is the door not opening? And I hear your sister laughing, like the stubborn person that she is. And she's now like saying that, oh, she's not going to allow you to enter inside the kitchen. That she has blocked the door and she's not going to allow you to enter the kitchen. So you now keep pushing and pushing and pushing because you want to be able to enter the kitchen. But she's applying another force on the other side of the door that is making it difficult for you to enter the kitchen. That force now that is working against your own efforts to open the door of the kitchen is now known as resistance. Do we get? Do we get? So in this case, resistance is the opposing force that is stopping you. And in this case now, you, in this case, you are the electricity. Hey, whoa. See ugly handwriting. You in this case now, you're electricity. The kitchen is the circuit. La, 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 la. Oh, this class is going to be very short. The kitchen is the circuit. The door, what is the door say? Let's say the door is a switch that goes open and close, on and off. The kitchen is, sorry, the door is a switch. And then your sister is now the resistor that is resisting all your efforts to open the door, like the stubborn person that she is, because she wants to frustrate your life. I'm speaking from experience. They've done this thing to me before. So me, I know what I'm saying. I know what I'm saying. So your sister, oh sorry, not resistance, resistor. Your sister in this case is now the resistor. You understand? So the amount of effort or pressure or force that she is using to obstruct or to resist, because I don't want to use the word resist, but let's just say that, okay, to oppose you, the electricity entering into the circuit of, in this case, the electricity flowing through the circuit, is now what is now known as resistance. Please don't mind my horrible handwriting on this screen. Is now what is now known as resistance. And the the electrical component that is used to do this, that usually does this in a circuit, is known as a resistor. So this thing that I can see here, this is a resistor. And I forgot to add this one. Yeah, so this is known as a resistor. And okay, let me write out some important things that I believe you should know. I forgot to add to the slides. Yeah, so let's carry this away. So resistance is measured in the units. Oh, resistance is measured in the units ohms. Who is the person that first came up with the phenomenon of resistance or resistors? So this is the symbol for resistance. I believe this is symbol for ohms. So resistance is, as I said, the measure of opposition to the flow of electricity in a circuit. And it is measured, the SI unit is ohms. It is measured in ohms. And the symbol for it is this. I think I should zoom in. Symbol for it is this omega sign. Yeah, that's ohms. And I think I've also forgot to mention this for voltage. Voltage now is measured. Oh my god, why is my handwriting so ugly for this thing? Voltage now is measured in volts. Voltage is measured in volts, and yes, voltage English. Voltage is measured in volts, and it can be symbolized using V. That is, yeah, that's it for voltage. Then for current, why is my brain doing in it? For current, the SI unit for current is amperes, or you can say amps for short. And yeah, it can be represented using the symbol A. Do you understand? Do you understand? I'll take that as a yes. Okay. Okay, so now let us go into more things about resistance and resistors, because I'm not going to give you half-baked knowledge, but I shall hope everybody's taking notes. So, resistors. Yeah, so resistance is measured in ohms, and as we are measuring it, we know that, of course, like these resistors are going to have different values for them, right? So there is a way for you to actually, you can use a multimeter to actually measure resistance resistance of a circuit, or resistance of um okay, sorry. So what was I saying? What was I saying? Okay, I was saying that resistors or resistance can be used measuring an instrument, or be a component known as a multimeter. Yeah, known as a multimeter. So this is a multimeter. Multimeter, as the word implies, multi, can be used to measure different electrical properties, voltage, current, resistance, sometimes also capacitance, sometimes also inductance. I'll explain what inductance and capacitance is if we have time, but it's not part of the things that I shall want to explain in this class, because I think that they are. So Yeah, they are used to measure different electrical properties, or electronic properties, such as voltage, currents, resistance, capacitance, and the likes. So, yeah, this is what a multimeter looks like. And if you want, like, you can actually buy them in your local market. Yeah, you can buy them in your local market. Yeah. So I now want to explain I don't want to explain how it is you can measure. You can measure, as I said, there are two ways of measuring your resistance. Either you measure it using your multimeter or you measure it based on calculation. Because I want to believe that a lot of us are very familiar with the resistor color code. Yeah, I want to assume that we are actually very familiar with it. But I'm still going to explain it. I'm still going to explain so that I know that everybody is on the same. Yeah, so everybody's on the same page. So this is the resistor color code. It may be, I don't want to believe that it's everybody's first time seeing, but if it's your first time seeing, it's no problem. So this is the resistor color code. And as you can see, it has like a range of colors, and each colors has a certain value allocated to it. Right. So there are two different types of resist. Is it two? Yeah, there are two types of resistors. There are the resistors that have four bands, and then there are the resistors that have five bands. Yeah, five bands. So based on the colors on that resistor, you can use that to measure the you can use that to measure the um you can use that to measure the amount of resistance. Is that right? Yeah, the amount of resistance on that resistor, or how much it resists the flow of electricity. So yeah, so as you can see, it goes black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, silver. I tend to ignore these parts, the gray, white, gold, silver, because most times they are used in cases of tolerance, and not necessarily the other parts. Most of the resistors I've seen, whenever they have gray, white, gold, silver, they are mostly used in like cases of tolerance, either for temperature or for measuring their distance. But a lot of times they are negligible, so you may not need to take them into consideration. So yeah, let me explain. So how it works is, if you are working with the four band resistors, right? If you're working with the four band resistors, you have to take into consideration the first measure of resistance. You have to work with the first three bands. That's how you'll be able to know the resistance that you're working with for that particular resistor. So if it has let's use the color here now, for example. So we have green, we have blue, and we have yellow. So how it works is, you take the color of the first band rather. Take the color of the first band, and then you look at the chart and then trace it to the color on the chart. And in this case, since we're working with green, we can see that green is 5. So let's assume now you take number 5. Let's let's go back to the way we were taught like this in secondary school. So we take number 5, and let's say you now hold it, and let's assume like the 5 is here. So you now take it and you put number 5 here. Then the second band, the color is blue, and you look at the charts and you're like, okay, for the second band, what number is blue, even though it's kind of the same thing in the first three places. You take blue and then you look at the number allocated for blue is 6, and then you keep it along with the 5. Remember that you have 5 for green before, and then you now have 6. So 5, 6, that's 56. Then you now take the third band. You now take the third band, and because now we are dealing with a four band resistor. Because now we're dealing with a four band resistor, we are going to take the third band as the multiplier, meaning that the number that we have for the first two bands, we are going to multiply it by we are going to multiply it by the value allocated to the third band raised that's yeah the value allocated to the third band. And how the multiplier works for resistors is that it takes times 10 raised to power something. So if you are working with black, we know that the number allocated to black now is 0. So if at any point in time black is now the third band when we're working with four band black is now the third band when we're working with the four band um when we're working with the four band resistor, we are going to take that 0 and take it that okay for multiplier, since multipliers are automatically times 10 raised to power something, and that something is the number allocated to that color. We are going to take it that okay, it is going to be times 10 raised to power 0 if it is black, and anything raised to power 0, as we all know, we are science students, anything raised to power 0 is 1 automatically. So if this third band were to have been black, you know that whatever number we got from the first two bands is going to be multiplied by 1. If at any point in time the third band is brown, we know that it is good now, and then since 1 is the number allocated to the color brown, it's now going to be times 10 raised to power 1. 10 raised to power 1 is 10, and then we multiply it by that 10 if the third band were brown. Then for the red number allocated to red is blue, times 10 raised to power, sorry, it's 2. I'm so sorry. The number allocated to red is 2. So if the red were to have been the third band for a 4-band resistor, we are going to multiply it times 10 raised to power 2, which is the number. So you guys understand the trend. So whatever number is allocated to that particular color, if that color happens to be the third band in a 4-band resistor, it's going to be multiplied by it. So 10 times, so that number, the number we got for the first two bands multiplied by number we got for the first two bands multiplied by 10 raised to the number that has been allocated to that particular color. Does that make sense? Or have I lost anybody? Do we understand? If I'm going too fast, please let me know. Okay, so I think everybody understands. Very good. Very good. Okay, so now let's come back to this example now that we've been giving. We have green, blue, or green, blue, yellow. We got 56, that's 56 for green and for blue, and then we now have yellow. So yellow, number allocated to yellow is 4. So we know that we are going to multiply this 56 that we got for the green and the blue by 10 raised to 4, which is 10,000. So automatically we know that the value given for this value given to this resistor, or the resistance of this resistor, is 56 times 10 raised to 4, which is 560,000. And then this tolerance now is now in cases where okay, the actual, like like when we do calculations, there's the theoretical value and then there's now the actual value. So what this tolerance does is that okay, as you've calculated it now, in real life, if you measure it with a multimeter, the value may differ, either plus 5% of the value that you got or minus 5% of the value that you got. So let's take for instance now you measure a resistor that is supposed to be 330 ohms, and then you measure it and then you now see that oh okay, there's now like an allowance, there's like, let's say minus 0.33 something 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 something, or 0.0033 something 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 along those lines. So there is, or maybe there is an addition or there's a subtraction. So that tolerance now is now like okay, the actual value in real life and the way it varies from the calculated value. That's what the tolerance is. And sometimes like it's very, very small. It's like Imagine you have like a gold band as the last one, and then you have 5%. 5% is 0.05, and 0.05 is kind of not so important. It doesn't really make a difference. So that's the reason why most times I'm just like, let's just ignore it. Like let's leave it. Let's ignore it because it's not so significant like that. It's not so significant like that. So yeah, that's why I tend to ignore it a lot of times. Like when I'm using, I tend to ignore it. So yeah. hmm So now it's the same thing. The same thing applies for the five band. The same thing applies for the five band resistor. The only difference is just that you just take it one step forward. So instead of it being just the first two bands that you take into consideration, you are going to take the first three. You are going to take the first three into consideration, and then the fourth band is now the multiplier. So if you have now, in this case, you have red. Red is blue. Orange, the second band is three. That's 23. The third band is violet. Okay. So the first band in this case is two, is red. So we know that the number allocated to red is two. The second band is orange, and we know that the number allocated to orange is three. And then we know that the third band is purple or violet, whichever one you want to use. And number allocated to violet is 7. So we take the numbers 237, that's 437. And then we now take the last band, the fourth band, which is black. And you know that black, the number allocated to black is 0. And since it is the fourth band for a 5 band resistor, we are going to multiply it by 10 raised to power 0, which is 1. So in this case, we know that the value given for this resistor is 237. That's 237 red, orange, purple that we got at the initial stage. Yeah, and then the tolerance, I think this is brown. So the tolerance is like zero point 0.0, is like plus or minus 1%, which is 0.01. You can ignore it as I keep saying. So yeah, that is it for resistor, resistance, and all of that. Yeah, so that is it. So now we've considered voltage, current, resistance. So you can see this simple picture used to illustrate it. You can see the voltage, which is trying to push the electricity through it. And in this case, in most cases, like people refer to current and electricity are the same thing. They can be interchanged, because at the end of the day, current is still the rate of flow of electricity, or it can otherwise be considered to be the electricity. So the voltage is pushing the electricity through this circuit. This tube is the circuit. And then this cowboy here is the resistance. And you can see he's wearing ohms. So all of them have their SI units, volts, amperes, ohms. And then this cowboy is now trying to resist the flow of this current, this electricity through that through these circuits. And that is what now makes this is a simple illustration. So if current is constant along these circuits, we can say that voltage is directly proportional to R if current in this circuit is constant. And then we now know that, oh, okay, V is equal to I being the current, R. So hence this formula that we are seeing here. So yeah. So next is power. Next is power. Are we together? Am I moving too fast? Have we understood so far? Is there anything I need to go back to? Okay. Okay. Hmm. Time flies. Oh. Time flies. Okay. So what is power? What is power? I use this picture of this the electric wires and transformer and everything, because it's like a good way of explaining and depicting what power is. So what is power? Power is the rate at which electric energy is generated. Okay. Power is the rate at which in this case, let's say electricity is generated, traveled, that's transmitted, or is consumed in a circuit. So, what am I going to use as an example? What am I going to use as an example? What am I going to use as an example? Okay, okay, okay. So let's use this as an example. So this is a light bulb, right? And as we all know, light bulbs have filaments within them. That is this bright orange things that we can see inside of them. And how is it that whenever they bring, whenever like let's say AEDC should bring light in our house, our light bulb is not able to turn on. That is through the electricity that is transmitted from whether the sockets or the wires to these filaments now in this light bulb. But for those of us who don't know, the generation of this electricity now, or the generation of this energy, is going to produce a certain amount of heat. And that heat now that is being dissipated. English. That heat now that is being dissipated can now be referred to as the energy that is lost. Energy that is lost to this person. Energy that this whole all I call it conversion. So the rate at which this conversion happens, that is electrical energy is now being converted what is known as power. So it is the rate at which energy is transmitted, converted, travels, or is consumed. That is what is known as power. And I don't really want to go into it, like deep into it, but I'll write out a few points to note about power. So let me share this part. Let me carry this part away. So power has a number of formulas. And a lot of times, like whenever we are dealing with electronics, it tends to be one of the topics that is ignored, because it is something that is derived from primary all the other primary elements that I mentioned earlier: the voltage, your current, your resistance, your circuit, everything. But for the physics that we remember from when we were in secondary school, we know that power is equal to energy consumed or uh, energy used divided, over the time taken to consume the energy. And we all know that this energy is measured in joules. That's the SI unit for energy. And then time is measured in seconds. That's the SI unit for this thing. So energy can also be known as work. So it can also be known as work done. Work done meaning the transmission or the conversion or the travel of electricity over the time taken for it to do that. And work is also measured in joules, time is also measured in seconds. So the SI unit for power, in this case, who can guess what it is? There are actually two, but there's one that is very, 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 very common. Who can guess what the SI unit of power is?
What?
Okay. Yeah, actually, yeah, you're correct. Yeah. You can mute your mic, yeah. The sign for power is what? If we should take like this noun that we've used here, if we take it in literal terms, can say it is joule per second, but then that is not exactly standard. So we know, so we can say that power is measured in watts, which can be represented using W. So the SI unit for power is watts. Have I lost anybody at any point? Are we together? Okay. Okay, so we're together. All right. All right. So that is power. So I was able, so this is a table. As I mentioned, like power has a number of formulas. It has work done over time taken, energy consumed per time. But then using the three basic components that we worked with earlier, using the three basic, that's voltage, current, and resistance, we can see that power is can be calculated using the amount of voltage in a circuit multiplied by the current in that circuit, the square of the current in a circuit multiplied by the resistance in that circuit, the square of the voltage divided by the resistance. And we can also see from that simple formula that I gave, the V is equal to IR formula earlier. Can also use that to derive can also use that to derive current, which is amperes, measure of current measured in amperes. Can also derive the formula from this whole power equation to get your current. Can also yeah, so as you can see here, if at any point in time you want to make current subject of the formula, everything is interconnected, so we can derive them from each other. Does that make sense? Does that make sense? Okay. 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 So at this point in time, we have now covered the first four fundamentals of electronics, and I've reached the most. Okay, this is like the first complex one that we're going to deal with. This is pulse width modulation. This is pulse width modulation. So please give me a minute and then I'll explain. So I think we can use this time to, maybe if at any point you don't understand what I said, you can call it to my attention. But let's just, yeah, just give me a minute. Okay, so PWM, pulse width modulation. What is pulse width modulation about? I can't explain it in sentence form. I can't explain it in sentence form the way I would without going into like the explanation proper. So I'm going to do that. And then once I do that in a way that makes it easy to understand, then I'll now give my own definition of what pulse width modulation is. Yeah. Yeah. So in simple terms, okay, I think I'm going to contradict myself here. Pulse width modulation just has to do with it's basically a phenomenon that allows you to convert digital signals to analog signals. So you can see here we have a bunch of rectangular or square, we have a bunch of rectangular signals here. And how it works is, okay, I think I should have done analog and digital signals first before going into this. Okay. Hmm. Okay. Okay. So let me come here. So excuse me. Let me come here. So this is an analog signal. This is a digital signal. Analog signals are basically signals that travel, that they are continuous signals that travel along a wave. So basically they represent how God, please don't let English fail me now. Let English fail me now. An analog signal is basically a continuous sine wave that is used to represent how electricity travels or a signal travels from one point to another, depending on the type of component they're working with. And then a digital signal, in this case, are signals that have just two states, being on and off. I don't know if I'm doing justice to this explanation, but let me explain more. Let me come to the mirror board now. Let me come to the mirror board. Let's make it bigger. Okay, this is better. This is better. Let me zoom in a bit. Yeah, this is better. This is good. La 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 la. Okay. Okay, so coming back to this mirror, we have an analog signal here, and this is the same way. Then we have a digital signal here, on, off, on, off, on, off, on, off, off. Okay, so this is analog, this is digital. How pulse width modulation works is that it is used majorly in digital circuits. Analog Jesus. I don't know why English is failing me. I don't know why English is failing me now, but pulse width modulation, as I mentioned earlier, is a way of you converting digital signals to an analog signal. When I say analog signal, I mean it in the sense that analog signals have varying values. So now you have a power source now here. This power source is 5 volts. You have positive 5 volts, you have negative 5 volts. And then this current in this current in this system or in this circuit travels, moves up, increases till it reaches the maximum value. And that maximum value now, in this case, since this is a graph, is known as the amplitude. And that amplitude here now is now the 5 volts. Then it travels, it reaches 4.99, 4.98, 4.9, something, 3 point something, it reaches 0. Then now travels down minus 0.1, minus 2.3, minus 3 point something, till it gets to this other amplitude, till it gets to this negative value, the highest negative value of this graph of this signal, which is minus 5 volts. Then it travels again, keeps going up, stops at 5, then keeps going down, stops at minus 5, and then up and down continuously. But digital signals don't work that way. Digital signals have just two states, and those two states are on and off. So let's assume now you are working with this same 5 volts now that is here. This same 5 volts now that is here. Imagine a switch. You know that a switch, there is no in between for a switch. The only instances that a switch can exist is just on and off, right? Just on and off. And then for that switch now, because that switch is a digital component or a digital electrical component, it has only two states, and that state can now only be on and off. Forget about all these ones under, because you can take them to be negative. I don't want to assume that a switch has negative this thing unless you invert you switch the polarity. But I doubt that that's going to be the case. So I don't think. Yeah, unless you switch the polarity and then the values now become negative, that it's now going from -5 to 0, -5 to 0, -5 to 0. When the normal case now that we now take digital values that, oh, okay, now it's traveling, and as it travels, it doesn't just go, oh, varies from any number between 0 and 5. It can only exist in a state of only 0 volts and only 5 volts. We understand. So now we now have these signals, like this signal here. It can only go on, off, on, off, on, off, on, off, like that. But the way pulse width modulation is that it allows you that, oh, even if you are working with a digital device, right? Even if you're working with a digital device or you're working with digital signals, you can now vary those signals. Let's use, for instance, you're working with 5 volts. Now, instead of it just going on and off, you can do it in such a way that, oh, you can actually stop at a value between that 0 and 5 volts. You can stop at maybe 2.3, you can stop at 3.5, you can stop at 4.5, or you can stop at 5 fully. And yes, it is a digital device, but now you now have the luxury of being able to choose whatever value between that 0 and 5 volts, if that is the maximum power source that you're working with. If that's the maximum power source that you're working with, you can now select a value between that range that will now allow you to now like operate and work with that digital component. Do we understand? So let me use like a real okay, so let me use a real world scenario now. Pulse width are used mostly in cases where you want to increase the brightness of an LED or a light bulb, or decrease it, or you want to increase the speed of a motor, a tire, or a wheel, or you want to decrease it. So let me come to this mirror board and explain now. Okay, no, let me not switch so fast. So pulse width modulations works using this thing called duty cycles. And these duty cycles are now what to now determine the gaps between the first cycle and the next one. So if now let's assume you are working with this kind of circuit, meaning that, oh, you can see that the distance between the off state, the on state, the off state, the on state, they are equal, right? They are equal. Are we together? Or am I talking to myself? They are equal. Like, even you don't need to use a ruler to, like, using your common eye this thing, you can see that, oh, the amount of time this circuit is, or this power supply or power source is off, and the amount of times it is on, they are equal. So in this case, you can see that the duty cycle of this particular circuit is 50%, because the amount of time the circuit or power is flowing through the circuit is equal to the amount of time that power is flowing, or that power is not flowing in that circuit. Do we understand? Have I lost anybody? Have I lost anybody? Have I lost anybody? Am I moving too fast? Okay, Chinedu, do you have a question?
I didn't get the last part of what you were saying.
Which part exactly?
The part on what do you call it? I didn't hear it clearly. Like so
The part.
the pulse
Mm-hmm.
width modulation stuff, the duty cycle stuff.
Okay. So what I was saying about duty cycle is pulse width modulation most times, like, they work using something called duty cycles, or they um take into consideration something that is called duty cycles. What duty cycles have to do is measuring the amount of time that current or electricity runs through a circuit in comparison to the amount of time that current does not run through that circuit. Do you get? So now in this case, now this particular circuit now that we're seeing here, we can see that you don't even need to measure it by yourself. You can tell that the on time for the power source and the off time for the power source, they are equal, because distance between the up and down, they are the same, right? Yeah. So you can now say that, oh, the amount of time that this circuit spent on and the amount of time that this circuit spent off, they are equal. So the duty cycle is now 50%, because the time that the power source was off and the time that the power source was on was equal. But then there are now cases where you now want to reduce the duty cycle. I know, you know what the implication of reducing or increasing the duty cycle is? You increase or reduce the brightness of this lamp that you're trying to control, whose brightness you're trying to control, or you increase and reduce the speed of whatever this motor or this wheel that you're trying to control. So let me come to the mirror this thing. Okay, let me come to the mirror this thing. So we know that computers work very, like, they move at a speed that is 1,000 times faster than the normal human eye. That's the reason why, for those of us who are conversant with, like, coding and programming, we know that we know that what term do I want to say? Those of us who are very conversant with programming and all, we know that whenever we want to calculate time, our own time, and convert it to the time that computers actually use, most times we convert it to either microseconds or milliseconds, right? And for those of us who do not know, microseconds, one microsecond or 1 second is 1,000 milliseconds. And then for micro now, I think 1 second is now 1 times 10 raised to 6. Yeah, 10 raised to 6 microseconds. So these are the values that computer systems use to calculate their own time. Because, as I keep saying, computers move at a speed that is far faster than the human eye. So a lot of times, whenever we want to make a computer system to work in a way that whenever we want a computer system to work in a way that is not too fast for us to see, most times we add like a delay of 1,000 milliseconds. That's 1 second our own time. So that when that computer system is carrying out the task that we want it to carry out, it's not be so fast that we can't see it. It's not be so fast that we can't see it. So whenever we add something called a delay to our code, or to whatever to our code that we're working with the computer system, we make the computer system to slow down so that our eyes can actually catch up. So why did I say this? Because this is exactly the same thing that happens in pulse width modulation. We increase the duty cycle, we reduce the duty cycle. Increasing and reducing, it basically increases or reduces the gaps between the on states and the off states of a this thing. Like now, look at this one now. This duty cycle now is probably a 25% duty cycle because the amount of time that this power source is off is 2 times as much as the amount of time that it is on. So we know that the power source here is 2 times the amount of time that it is off is twice as much as the amount of time that it is on. And what this does is that as it keeps traveling and oh my days, it makes sense now. Okay, so as it keeps reducing, imagine something that is traveling so fast, but then the off state is far more than the on state. How do you think it is going to appear to the human eye? It is either going to be dimmer or it is going to be slower. Am I correct? Do you agree with me that that's what is going to happen? So that is how pulse width modulation works. If now, let's assume I'm working with a knob, let's say a potentiometer. Let me show you what a potentiometer is. Let's assume I'm working with a knob like this that I can use to actually increase the speed of the motor. Okay, so Isaac, you have a question?
Sorry, can you hear me?
Yes, I can.
All right, please go back to the last slide. Sorry. Okay. On the PMW signal, the second image, the gaps in the amount of like the off whatever, it doesn't seem to be consistent like the one on the left. Is there a reason for that? Maybe because I'm not sure if I understand.
Are you making reference to the first one, this one here, or the second one here?
No, both the PNW signal both. On the left one now is the gaps, the off states, the amount of time is off is consistent for each wave. But on the right, it's not consistent. Some are shorter than others for the off states. Why?
Mm. Okay. Um.
Thank you.
Okay. No, I've not even answered the question. You're already telling me thank you. Okay. So this is a completely different example because this is assuming, as you said, like it is inconsistent, right? This is assuming a case where let's assume like as I made mention to this knob, let's say that this knob, this potentiometer here, is what is controlling how these circuits in this system is traveling, right? Let's assume that. Mm. So if now we come here, this is just like a different example, right? And it is working in line with based on how this particular wave is traveling. So now you start here, you start on a high note. The pulse width modulation takes the average, like the average, what am I going to say? The average, coaching, the average signal that is being sent to these electrical components. As I said, I'm still going to make reference to the light bulb or the motor, right? So as it keeps traveling, or as the duty cycle keeps increasing and reducing, whatever, this modulating signal is going to travel, right? It is going to travel. Now, what this pulse width, this PWM signal is doing, what this PWM signal is doing is basically just interpreting what this sine wave is doing. Do you get? Do you get? Yeah. So basically, what this pulse width modulation signal is doing, it is trying to represent what is going on in this sine graph or in this sine wave. So it started at a very low point. Look at this side here. As I said, pulse width modulation is basically in my own words, a way of you converting digital signals to analog signals. And I say analog signals because analog signals can vary. They can vary from 0 to 1023. If you're familiar with analog signals, that's how they travel. So the reason why I say analog signals is because digital signals don't usually vary. Like they don't have a range of values that they take. Analog signals are the only ones that do that. And now, pulse width modulation allows you to be able to do that with digital signals. So as this pulse width in this top part, these pulses are traveling. It is now creating an entire this whole sine wave that is now being interpreted as the speed or the brightness of the light bulb or of the motor. Now, this pulse width modulation signal is now interpreting what this sine wave is doing. That okay, it started at a point of 0. See this point 0 here. Started at a point 0 here. So it started at an off state. So now it's gradually going up and then it went up. It went up. And then now it's now coming down, meaning that it is decreasing. So as it decreased, because digital signals don't have anything like, oh, it decreased, it is off. So the pulse modulation will now take like the average time that this thing was on here and now translate it to this graph that is here. Does that make sense? Does that make
Okay,
sense? I still need to. Mm.
just so I understand,
Mm-hmm.
the what do you call it? The on states are used to describe the signal get increasing or whatever. I'm not sure if I'm using the right English,
The
and then
amount of time. Yeah. Okay.
yeah,
Something like that.
and then the off states are when the signal is this thing going down.
Mm-hmm.
Okay, thank you very much.
So basically, it takes the average of that on time and that off time and now translates it to either brightness or speed. You get? Do you understand? Okay. All right. So what this pulse width signals is just doing is that it's interpreting what is going on with this graph, this sine graph. That's what it is interpreting. And then these pulse carriers are just explaining to us the amount of on time, off time, blah blah blah, along those lines. So it takes the average of this and now like translates it to brightness or speed. I use brightness or speed a lot because I feel like it's the one that we can understand the most. The example that we can understand the most. So uh yeah, so that's basically what pulse width modulation does. And it measures this signal, it takes these values from a range of values of 0 to 255. I will explain why it's 255 in another class, but not today. Not today because I want us spend I want us spend 2 hours and we have not covered sensors. So any other thing that if we have extra time, I'll come back to this. So yeah, a range of values from 0 to 255. Yes. And that's because of the la 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 English. That is because as these signals travel, it is taken into consideration the amount of God abeg, the amount of, will I say, storage capacity that these digital components can occupy. So I mentioned earlier that analog devices they work using a range of 0 to 1023. I'll explain why 0 to 1023. But now we know that using, I'm going to make reference to computer science that we learned when we were in primary school. We know that how these signals travel, because we're working with computer systems, how these signals, and we're working with digital analog devices, components, computer systems, microcontrollers, all of that. These signals travel in a computer system, and this computer system is a digital system. We know that digital systems send data using bits, bytes, and the likes. So if now we are going to take into consideration that, oh, this is actually a digital device, right? And making reference to computer science that we learned when we were in primary school, we know fully well that one byte, a byte is probably the one of the smallest amounts of one of the smallest units of, oh god, English language, one of the smallest units of let's say signal or storage capacity. Let's just say that the smallest unit in which data travels, yes, data travels or is stored, is known as a byte. One of the smallest unit, but smaller than this byte, we now have bits. Bit is now the smallest, and we know that 1 byte is equal to 8 bits. If we remember our computer science in primary school well. So since we are dealing with digital devices, we know that since we are dealing with we're dealing with digital devices. Now, there was a point in time when they mentioned that, okay, if you want to calculate the storage capacity of you want to calculate storage capacity of a digital device, all you have to do is do 2 raised to n. Well, in this case, that n, which is we're going to be using bits, because now we are sending data, we're sending signals to digital components. So now we are going to now translate this 2 raised to n to 2 raised to power 8, because we're working with digital design. What is 2 raised to 8? What is 2 raised to 8? Can anybody do the calculation for us? What is 2 raised to power 8? 2 times 2, 2 times 2. Oh my god. This stressful. Sure? Nobody have calculated it. I have to do it by myself. Oh, wow. I feel like people are bored. Anyway, 2 raised to
256.
8. Thank you very much. 2 raised to 8 is 256. 2 raised to 8 is 256. But since computer systems, now we have 256 as a value. But then since computer systems start counting, we human beings, when we are counting, we count 1, 2, 3, 4, 5, 6. Since computer systems start counting from 0, for it to be able to travel 256 steps, it is going to be from 0 to what? 255 as a computer system. If we're to be human being counting, it will be 1 to 256. As computer system now is from 0 to 255. Does that make sense to us? Does that make sense to us? Do we have questions? Are we lost? Are we lost? Can you don't ask your question?
I didn't get clear. You said computer something something. I didn't get that part clear.
I said that computer system. Did you understand this part?
Yes, I did.
Okay. I said computer systems. Human beings, when we are counting something, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right?
Yes.
Computer systems start counting not from 1, but they start counting from 0, right? So let's assume now I'm a computer and I want to be able to count to 256, or I want to take 256 steps as a computer system, but I'm starting from 0. Where am I going to stop? Where am I going to stop?
So my network is lagging.
255. If I'm a computer system and I'm counting 256 steps, and as a computer system, I start counting from 0, I am going to automatically, if I'm going to count 255 steps, I'm going to stop at 200. Sorry, I'm taking 256 steps. I'm going to automatically stop at 255. You understand?
Yes, I do. Yes, I do.
Okay. So yeah, that is that. That is that. So that is why it stops at 255. That's why. So next things next. So pulse width modulation is used in cases like let's say you want to increase and decrease the brightness of an LED. Uh, mm, yeah, it's used in cases where we want to increase and decrease the brightness of an LED. It is used in cases where we want to increase and decrease the speed of a motor. Yeah. So yes, cases like this. So you can see this knob here, and you can see how. Let me zoom in. You can see this knob here, and you can see how you can use this knob to increase and to decrease the brightness of this LED here. So that is one good example. You can also use the same knob to increase and decrease the speed of a motor. So yeah. So now let's move on to the next thing. And I think we'll stop here and probably schedule on that class for this because we still need to cover inductors, capacitors, what else again? We still need to cover inductors and capacitors. We still need to cover okay, I think that those are the major things. We still need to cover battery life and efficiency. There are other things that we need to cover, sure, but I think we'll schedule another class for it. I don't want to oversaturate everybody's brain. So I think that's where we'll stop. I think we'll stop here at sensors and then we'll move forward. Yeah, because I want to keep it to 2 hours. And yeah, I want to keep it to 2 hours. Then if we need to schedule another class, no problem. Like I like to teach and I want to make it as understandable for everybody as possible. So yeah. So sensors. What are sensors? The same way we as human beings, we have our eyes, we have our nose, we have our mouth, we have our tongues. Sorry, this was supposed to be tongues. We have our eyes, we have our nose, we have our tongues, we have our ears. Sensors are those sensory parts of any project that receives external stimulus from the environment or from any external factor. That is what sensors do. So the same way I have eyes and I can see, I have a nose and I can smell, I have a tongue and I can taste, I have the skin and I can feel, I have my ears and I can hear. And I'm receiving data from different external um different external um external yeah different things are happening in the environment. That is the same way sensors can receive all these data, whether physical, whether chemical, whether electrical, whatever. Sensors can receive them and then translate them into data that the computer system can understand. So that's what sensors are. So these are different type of sensors. We have color sensors, we have touch sensors, ultrasonic, humidity sensors, temperature sensors, gyroscope and accelerometer sensors, flow sensors, speed sensors, rain sensors, and so on and so forth. So this is where the analog and digital signals come in. Sensors can be divided into two parts. We have analog sensors and then we have digital sensors. Analog sensors are the type of sensors that analog sensors are the type of sensors that they receive they measure physical conditions. So things like how much a thing is bent, things like light, things like sound, they measure them. So the same way like your eyes, your nose, your mouth, everything can be able to sense what is going on in your environment. That's the same way analog sensors can be able to sense those different phenomena and stimuli happening in the external environment. The digital devices, can do what analog devices do, just that they have more capabilities. They can measure physical or they can measure physical. I'm so sorry, English is failing me a lot these days. They can God. They can measure physical, chemical, electrical conditions, not just physical conditions like the analog distance, but they can also measure chemical they can measure chemical, they can measure electrical, um they can measure sound. You guys shall understand what I'm trying to say. So I don't know why I'm biting my tongue these days. I don't know, but maybe it's because I don't talk so much. Sha. Yeah. And they exist in two states. That's on off. So analog sensors, they have a range of values. Like now, whenever if for at any point in time you want to work with any of these sensors, if you're working with a microcontroller, you have to work with the analog pins of that microcontroller. Microcontrollers have analog and digital pins, and those analog and digital pins, they are what allow you to be able to read data from they are what allow you to be able to read data from analog devices or analog sensors in this case, and digital sensors. So let me just quickly show you. Like, I don't know if you guys can see this picture clearly. Let me just try to zoom in. Yeah, let me just try to zoom in. Coaching, where did you go? Yeah. So the way we have this Arduino now. This Arduino has this is a microcontroller, by the way. This is the small computer on a chip, or the small computer on a chip that you can or work on your projects that you work on. So pins, these are the ones that have just pins. These are the ones that have a attached to the front of them. So these analog components or analog sensors, analog devices are going to be connected to the analog pins of this microcontroller here. So this is what now allows us to be able to read range of values from 0 to 1023. Yeah, that is what allows us to do that. So let me come back here. So the digital devices, they just have on-off states. Oh, this is a flame sensor. Flame sensor, is there fire? On. Is there no fire? Off. Push button. Is the button pushed? Off. Is the button pushed? Yes. On. Is the button not pushed? No. Off. Or you can reverse the logic. This is a relay. A relay is a component, is a like an electrical a switch that can be an electrical switch that can be programmed. So you can program it to come on and off where when any you can program it to come on and off when any condition is met. Yeah. So, or when you want it to turn on and off based on any period of time, at any point in time. That's what a relay does. So you can program it whether, oh, okay, if so and so condition is met, come on. Otherwise, turn off. Or, oh, after so and so seconds, turn on, turn off, turn on, turn off, turn on, turn off. So this is a relay, and this relay allows you to electrically control on off commands. Then this is not a sensor, but this is also a digital device because LEDs have just two states, on and off. But you can also program them using pulse width modulation, um, to vary the brightness of them. So are we together? Are we together? I can move on. Okay. Okay. So as I mentioned earlier, digital devices have just two states, on and off, on and off. I don't think this graph is even a good example. This is a better example. On, off, on, off, on, off. Then analog devices travel along a sine wave. So they have a range of values, positive, zero, positive, zero, negative, zero, positive. So that's how their signals travel. And the range of values that you get for its data, they vary. What are the differences now between analog sensors and digital sensors? Analog sensors can read data using a range of values between 0 and 1023. I'll explain why very soon. They measure physical quantities such as light, temperature, pressure, etc. Their signals are represented in form of sine waves. This is a sine wave. So this wave that we're seeing here, that's sine wave. For digital devices, they have just two states, except the only exemption is when you're using pulse width modulation. But normally, they have just two states, that's on and off. They can measure physical, chemical, or biological properties, and they operate using discrete and digitized data. So this is discrete data. There is no in between. It's just on and off. Just on and off. And the signals are represented in form of square waves. So this square waves, not the flowing like water sine wave that's here, but square. Just on, off, on, off, on, off. So now to round up, because I think time has been fast spent. Now next class I'll try to go more in depth and cover inductors, capacitors, and the rest of them, and then we'll probably do more circuit work so that when you guys are doing more designing of circuits in PCBs, you guys can actually follow along and know what is right and what is wrong and what is possible and what is not possible. Yeah, so as I mentioned earlier, let me come back here and explain why the analog values are from 0 to 1023. So as I mentioned earlier before, I said that computer systems store data in bytes or bits, and the smallest unit of um, data that data can be stored or data can travel is bits. The second is bytes. So as we all know from our this in secondary school, as I keep making reference to, 1 byte is 8 bits. But now let's go further, let's go deeper. After bytes is what? Who can guess? What is the next
Kilobyte.
biggest? Hmm?
I think it will be kilobyte.
Yes, exactly. Exactly. Kilobyte. Sorry. So after bytes, we have kilobytes. And if we remember well, you know that 1 kilobyte is what? 1024 bytes. True or false? True. Exactly. After kilobytes, we have what?
Megabyte.
What?
Megabyte.
Mm-hmm. Mm-hmm. Okay. Here's my mirror. Okay. So after kilobytes, we have megabytes. 1 megabyte is also 1024 kilobytes, or we can represent using KB. After megabytes, we have gigabytes. And we know that 1 gigabyte is what? 1024 megabytes or MB. And then after gigabytes, if we want to go deeper, we have terabytes. And 1 terabyte is also 1024 gigabytes. Then 1 petabyte, if you want to go deep, 1 petabyte is 1024 terabytes TB. So if you look at it properly, you'll notice a trend. 1024, 1024, 1024, 1024, right? 1024 is a very big something. So you can assume that one of the maximum capacities for storage or for data to travel for digital components is 1024. You can assume that, right? 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 Or have I lost anybody? Okay. We can assume that. So earlier I mentioned that if I am a computer system, and as a computer system, I start counting from 0. Let's take this 8 byte self now, for instance. And this is my storage unit for my computer. And now, maximum capacity that I have is 8 bits. So automatically I have 8 rooms. So 1, 2, 3, 4, 5, 6, 7, and 8. So I have 8 rooms as my storage units. And as a human being now, I want to start counting. Okay, as a human being, 1, 2, 3, 4, 5, 6, 7, and 8, right? But then I don't want to use human being terms because I'm working with a computer system. And a computer system will never start counting from 1. The computer system will start counting from what number? From 0. So, as a computer system now, I have 8 rooms, but I'm going to count as a computer system. I'm going to count from 0. So I say 0, 1, 2, 3, 4, 5, 6, and 7. There are still 8 rooms. But because I counted the way a computer system would, I stopped at 7. Now I noticed this trend and I'm like, oh, okay, now I have 1024 rooms. And I'm not going to start counting from 1 because I'm making reference to computer system counting. So I'm going to count from 0. And I'm going to count it like this. Da da da. So from 1024. But since I'm counting from 0, I'm going to count 0, 1, 2, 3, da 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 to 1023. Why did I stop at 1023? Because I took 1024 steps. But because I started counting from 0, I'm automatically going to stop at 1023. So as a computer system, in relation to how human beings count, I'm not going to count the normal way human beings would count. I'm not going to count the normal way human beings are going to count. I'm going to count the way a computer system is going to count. And that is what will now make me stop at 1023. Does that make sense? Do we understand? Have I lost anybody? Are we together? Okay. So I think we'll stop here for today. And then tomorrow, and then probably tomorrow I will reach out to your teacher for PCB design class, ask him if he's going to be available tomorrow. We should have PCB design class tomorrow. So I'm going to communicate with you guys, as I said, and try to reach out to him. Then before 12 noon tomorrow, I should get an answer, and then I'll let us know. We will probably have the class by 4 p.m. tomorrow evening. So let's just bear that in mind, and let's just get ready. And then with the little that we shall learn here today, let's try to at least develop and grow and build on it. So does anybody have any questions before we call it a night? I think I asked all the questions. Or you guys asked all the questions while we were having the class. So nobody has any question. I think I explained very well. I explained it very well. All right. So I'm going to call it a day here. And in our next class, we'll probably have another class during the course, maybe at the middle of the week next week, because next week your embedded systems instructor is going to take over. So everything that you learned here today is going to apply to your PCB design class and your embedded systems class moving forward. So if at any point you are lost, just make reference to this. I'll be sure to send the slides to the group chat, and then also make the recording available. I'm really sorry. I know that I've been defaulting in regards to the recording and everything. It's just that the recording for the last class, I've not exactly been able to upload it to the Google Drive since, because of like it's very heavy, and I don't know, every time that I shall try to start uploading it, it's never, I don't know, like it always stops in between, maybe due to connection problems or something. But I'll do my best before the end of this weekend to get it up. But the recording for the first class is already on, but I won't send the links for both classes at the same time. So please, you guys should just bear with me for the time being. And as soon as the recording is available, I'll be sure to send the links. Then you can now request access, and then I'll give you access to the recordings, and then you guys can watch it so that you can catch up, or if you need to make reference to anything at the end of the day. So yeah, thank you guys so much for joining. We'll meet in the next class. If you have any questions, my DM is always open. I will be at your beck and call.
Yes, ma'am. I'm still expecting the recording for the last class.
As I said that the reason why I just suggest that the reason why it has been taking a lot of time is because I want to send the recording for the first and second class together. But then I think because the recording for the second class is actually very heavy, so every time that I try to upload it, it always stops or cancels in between. I don't know why, maybe network or something, but want to keep trying, and I'll send both the links for both recordings at the same time. And then as soon as both of them are ready, I'll send the links, then you guys can request access as viewers, not editors, please, as viewers to the recording, and then you guys can watch the recordings, go back to it, make reference to it, and all of that. So yeah, I think this brings us to the end of our class for today. We'll have PCB design class hopefully tomorrow. I'll be sure to communicate it before 12 noon. But please bear it in mind that we have PCB design class tomorrow by 4 p.m. So I think we can call it a night here. Thank you guys so much for staying to the end, and see tomorrow. We'll see tomorrow. And if you have any other questions, please be sure to reach out to me. Type. So good night, everybody, and have a wonderful night's rest.
Good
See you
night.
guys tomorrow. Good night.